All right. So Sir Isaac Newton, dude, he observed the rules of motion as he observed them, and urban legend has it that as he sat under a tree pondering, an apple fell out of the tree and it hit him in the head. Gave him 3 ideas. The first one, that an object in motion, you should be able to probably fill these out without my help, but an object in motion stays in motion. Thursday, which seems like about 2 weeks ago already, but last week, Thursday, we were in the gym with mallets and bowling balls, and what you should have noticed is that once you gave that bowling ball a push, it kept going all the way around the gym. It would not stop until it hit the wall on the other side of the door. The second thing, force. Only a force can change the inertia of an object. And that was what we were doing with the mallets, those rubber mallets. You'd have to smack that bowling ball to change its inertia. If it was sitting still, you had to smack it to get it moving. And if it was moving, you had to smack it to get it to stop. But only a force like that would stop the object. Otherwise, it just kind of kept doing what it was doing. The third law is what the next packet, Unit 6, will be about. But because we're talking the first and second, we might as well put them all 3 here, and because you already know them anyway. The third law of momentum: for every action, there is an equal and opposite reaction. Equal and opposite reaction. Maybe you noticed that when one bowling ball banged into another one, there were reactions that happened, and they were equal and opposite. These 3 laws, they seem kind of simple enough, no big deal. Why is he such a big deal? But the first law was commonly understood at that time. An object in motion comes to rest, because that's what's obvious. If I throw a Frisbee, it comes to rest every single time. Never have I thrown one and it just kept on going forever. And if I roll that bowling ball, I know eventually it is going to come to rest. It's either going to bang into something, but it's not going to go forever. But he was one of the first people to really start looking around at with telescopes, and understood that the orbits that were happening up there with Jupiter and Venus and whatnot, that those things, they did not slow down. They just kept going at the exact same speed. And so the math that he had at that day didn't really explain what he was observing. And so he just went around and invented calculus. For those of you that are strong in math, not me, if you're taking pre-calculus or calculus, it's not easy stuff. Well, Newton just invented it on his own and said, I think I need to know this is the math that will help me explain where planets are going to be. In his quest to understand light and rainbows, he also discovered invisible light. He took, because they were understanding glass and that you could make prisms and you could then make rainbows. If you get the sunshine in a prism, he could make a rainbow. And his curious question was, is like Roy hotter than G. Biv? And he put thermometers in each of the colors of the spectrum and found that they were all about the same, no big deal. But then the sun moved, or actually we moved, and then his rainbow moved, and on the outside of the red, it was getting hotter. That would be the infrared, or the night vision or heat vision, we call it, but that's a hotter frequency of light. And so he discovered invisible light just by accident. That's the kind of dude he was. Anyway, got some thinking questions here. 2, closed containers. Let's pretend they're like bowling balls. If you've got a bowling ball, they look the same, but one of them's packed with lead and the other's packed with a few feathers. There's going to be a noticeable difference in how they behave. If you could determine which one was more massive, if you were out in a weightless condition in outer space, so you're floating around in the space station, and neither of them weigh anything, how could you figure out which one was more massive? And I would say is to give them each a shove, push. Well, let's use a better word. If you give them a force, if you give them a push, if you give them a large push, the more massive one, which would be the heavier if it's on Earth, but the more massive is going to equal less motion because of the idea of inertia. If it's just not moving in outer space and you want to give it a push, you're going to have to change its inertia. And if it is full of lead, it's going to be harder for that thing to get moving than if it was full of feathers. So you end up with kind of an inverse relationship. More mass is less motion. Less mass is going to equal more motion. And so we're going to end up with kind of like an inverse type relationship. All right, I'm coming back out of this. I'm ready for messages. Let's hear what blew away this weekend. What did you have to tie down? And you may speak if you want to speak. Mr. Workman, did you lose anything?
There's always that pause to unmute, you know. No, we didn't lose anything. It sounded kind of creepy at night with the trees banging around, but everything was still intact the next morning, even the trampoline.
Tree branches, pillows on the front porch couch. Yes, they would be gone. Trash can, mine tipped over.
Yeah, we must have been lucky.
We lost a cat.
You lost a cat?
Yeah. A gnome fell in the lake. Nice. I love it.
We had to put a tarp over everything on our deck and put bricks on the tarp.
Huh. I put chairs on top of our fire pit, the tarp. I strapped my grill down because we just bought it. And the last time I bought a brand new grill, it lasted about a week and the wind blew it over and dented it all up. And it was that way forever. I was mad. All right, going back. What path would the moon take if suddenly no gravitational force from Earth acted upon it? Let's just pretend all of Earth burned up in the 2020 dumpster fire and it wasn't here anymore, it was gone. The moon was following a path that was like going around the Earth. So if it was in like a circular path like that, and then all of a sudden there was no Earth, you would then, if that at that point right there was no more Earth, the moon would just continue in a straight line. Maybe you noticed that when you were rolling the bowling ball around the 3-point line in the gym. Like if you weren't pushing on it, if you were pushing on it, you could get it to go in the circle. But as soon as you quit pushing on it, it would do the straight line. Number 7, why is it more difficult to push a stalled car from rest than it is to keep it in motion once it's rolling? And that's going to come down to that idea of inertia again. A stalled car has to change inertia. And it's going to require a force. You're going to have to push just to get that thing moving, to change its inertia. But once you get it moving, it's a lot easier to keep it moving, assuming there's not much friction. Now, a car has a lot of friction with its tires and everything like that, but keeping it moving is kind of like that bowling ball in the gym. Once you get the thing started, it doesn't take much to keep it going because you're only fighting friction. So if you're keeping it moving, you need to overcome friction. Not inertia. It'll already have, once it's got its motion, the inertia is to just keep doing what it's already doing. It wants to just, I shouldn't say the car should want, but it will just keep doing what it was doing. Okay, astronauts while traveling to Mars. It's a 3-month trip at 11,200 meters per second. That's fast. That is more than a 10K per second. So that's like, you're talking like 7 miles. 7 miles in 1 second. Odds are right now you are probably less than 7 miles away from me, and we're far apart. And that means that the space shuttle, or whatever rocket it's on its way to Mars, can travel from me to you in a second. That's quick. I can't imagine traveling that fast. Anyway, we've got these astronauts, and they're heading off to Mars, and they decide, let's just send our trash back to Earth. We'll launch it at 500 meters per second back to Earth. So you've got you and the trash going 11,200 meters per second. I'm just going to try to make that into a vector. And then, so you and the trash is traveling to the right or to Mars. And then you decide that you're going to launch it backwards at 500. 500 is not very much. That's a small arrow compared to the 11,200 meters per second. So I think that what's going to happen is, if the trash was doing 11,200 to the right and you just sent it 500 to the left, it's really going to be going, I should make that appropriate, 10,700 meters per second to Mars. It's still going to Mars. You're going to have to send it back more than 11,200 to get it to go all the way back to Earth. It's like the bowling ball moving along and you give it a little tap backwards. It doesn't mean it just starts going backwards. All it means is that it has less forward. So what happens when they get to Mars? After you land on Mars, the trash lands on you. Sorry, my penmanship's getting bad off the bottom of the paper there. So that's kind of the notes version of today. What we would like to do then is try to introduce you to a unit of measurement that's going to become kind of common here in the next few weeks, and it's called the Newton, named after Sir Isaac. That's why we were kind of talking about him today. Newton measures a push, a force, and gravity is also a force. And so what we're going to do is lab 2. I know it's out of order, sorry, but as I did both labs, I figured out that lab 2 is probably better to do first. And all it is describing the relationship between grams and newtons. And so I made a video of me collecting the data so that you can watch that and collect your own data. You may, if you would like, put your data on a regular piece of paper or print this lab and put it on there if you're fine. But I would love it if you would use graphical analysis. That's off of that little button, the little round circle. You push on that and you type in G and graphical analysis will show up. That way you can put the X and Y values in there and you don't have to, it'll do the Y equals MX plus B for you so that you don't have to do all that math. But if you like doing the math, you go right ahead. And then I'm going to ask you to upload a nice pretty picture of your data, including your Y equals MX plus B, the questions and answers that are on that lab. I think there's 7 questions on there. And like I said, you should be able to upload that in the next half hour and not have any homework or anything like that. If you decide you want to upload it tomorrow, I'm probably going to ignore it unless you get in contact with me and let me know that there was some reason, like your Chromebook blew away in the storm or something like that. Mr. Workman, is there anything you'd like to add?
Yeah, don't come contract.
Okay. Okay, Mr. Workman is going to talk to you for a second. I'm going to stay on this meeting for as